So I want to do something in this talk that's very exciting to me. So let me just do maybe a quick recap of where we are and what one of the themes I want to hit. And so the quick recap is we had the Grothendieck-Lefschetz formula, or trace formula, and it's that for x, a smooth variety, that you can count the number of FQ points. This is algebra on this side. And on the other side, I'll do the compactly supported version. It's like q to the complex dimension of x, q to the complex dimension of x, times summation minus 1. It's like a fixed point thing here. Times, trace of Frobenius, acting on compactly supported cohomology of x, sort of FQ, whatever that is. And we were able to compute this, converting this to topology, the cohomology of the C points. And there was this dictionary between topology and arithmetic, the first entry of which is classical, which is understanding, say, the topology of x, but let me just say the cohomology of x with just rational coefficients on the one hand, and point counting. This is like André and Grothendieck. Then this kind of theme that you now have a sequence of spaces or groups or varieties. In this case, sequence varieties, and you want the cohomology of the nth one, the C points, to you look at it as n goes to infinity, and you want it to go to a limit. This is homological stability, that it stabilizes. Not just that it goes to a limit, It stabilizes, meaning for a fixed I, it stabilizes. Once n is bigger than I, it doesn't depend on n. And then over here, and this one we didn't talk about in the lectures. There's beautiful notes by Jordan Ellenberg in a past like Arizona summer school. And there's also
Winter school.
Arizona winter school, yes. It's a summer school to me. And there's Venkatesh has a talk at the ICM in 2010, asymptotic of the number of FQ points. So these are as n goes to infinity. And this is more speculative, and even more speculative still, although I showed you a proof of concept, I hope, yesterday, is that representation stability gives like the weighted point counts. And it's not just like, oh yeah, it's a weighted version. It's a completely new kind of, I think it's a new kind of thing, but in weighted point counts where the weights are by characters, and the character of the trivial representation gives classical stability. But you could plug in these characters and you get all these other problems with the expected number of linear factors and all these other statistics. Okay. That was basically what I wanted to give in terms of the bridge. What I want to do today is to think of this two-dimensional grid here. And there's more entries in this. Like I mentioned that the stable range, which is purely this kind of topological thing, I think this is a pretty cool thing, gives like error terms in asymptotic point counts. I didn't talk about this, but I just wanted to say for the experts. What I want to do today is do something that is quite known here, is super speculative here, and is like just not even, it's speculating on speculation here. But it lifts this whole picture. And it's based on this dream of Grothendieck and Deligne and others of something that would explain the miracle that goes between the topology of the complex points and the number of FQ points is this massive miracle involving all this stuff I'm putting under the rug. And they said, well, the dream is the theory of motives, which is which I don't know very much about except for a special shadow of it. But one object that would explain both things at the same time, the complex points and the FQ points. It's not going to live either in the complex world or the FQ world. There should be some other world. So I think there should be this next layer building out. I should think of it as up. Building up, where there's a motive story, which is one central thing, and then it will explain this. And then there should be stable motives. It'll explain this. It's the work of Akil Wood, like speculations, recent speculation. And then there should be FI motives, representation stability at the level of motives. Because this representation stability, it was for cohomology with complex coefficients. But really what we do in our paper, the Church-Hellenberg-Farb paper, we also prove that étale cohomology groups are representation stable. And there's a whole story there. So I want to show one really cool thing. And what's great is, well, the general theory of motives is way above people like, you know, I was going to say people like us, sorry. At least people like me. There's a reflection. So I want to, so lifting it all to motives. And everything I'm talking about is sort of a joint project ongoing, lifting it all to motives. And not just to generalize both things, but our take on it is, wow. And it's all going to be about this. Everything I'm going to talk about for the rest of the day is about lifting just this aspect. And which with Jesse Wilson, it's all with Jesse Wilson. It's been extremely exciting because we found it to be a very powerful computational tool for concrete computations. Even if you don't care about motives and you only care about this or you only care about this, motives is the way to get right. In fact, we didn't care about motives in the beginning. We just cared about the other thing. So let me explain what it does for you. Great. It's really looking at like one object with three glasses. You know, you have a variety. I'm always going to have like a smooth, again, but not compact. Most of these moduli spaces are like never compact. Smooth, variety, and let's just say it's defined over Z. It's cut out by a bunch of polynomials, at least locally, and the coefficients are in Z. Smooth variety over Z. And there's like three glasses. Jesse mentioned this in his talk. You can look at it with FQ glasses, FQ bar glasses, and C glasses. And you see the same thing in three different ways, but it's still the same thing. And the other theme in Jesse's talk that I'll hit on is, if you know about the topology of a space, like the space of polynomials, it's also an algebraic variety. That should have like deep implications about the topology. That's an old theme. So let me talk about the varieties I want to talk about. You're going to get something that's not poly n. Let me discuss the varieties. The first variety been studied for a very long time, but it's really a paper of Siegel, who explored the stable integral homology of these. So it's stable only for the ith homology for n large, or actually for d large. This is defined to be the space of holomorphic or algebraic, same thing, degree d maps phi going from P1 to Pn. Degree d just means you take the first Chern class here, pull it back, evaluate, you get d. If you don't know what that is, it's just rational maps from the Riemann sphere to the Riemann sphere, quotient of two polynomials. So, and the star is I want to take the point at infinity, so 1, 0, to the point 1. It's based maps. I'm just doing this for convenience. You can unbase it, but this is simpler. And you can do, and this is equal to the space. So this is the definition. This is just the space of n tuples of polynomials. So if you want to pick n equals 1, it's the space of rational maps from P1 to P1, a massive topic in dynamics. In the last 10 years, it's been a great topic, arithmetic dynamics. Like Silverman has even a whole book on arithmetic dynamics. And it's the case when n is 1 and the field, OK is any field. Oh, and I probably want a perfect field, but let me just ignore that. That's like finite fields and C, so I'll be fine. I want to look at where these are fi of z equals z to the, I want them all to be degree d. Right, so z to the d plus ai1 z to the d minus 1 plus aid. So they're polynomials where ai is in your field. You can take the complex numbers. And I want that they have no common zeros. of z, zeros, intersection of the zeros, sorry, sloppy. The intersection over all I of the zeros of the polynomials is the empty set. So for n equals 1, what this is, it's a rational map. What's a rational map? It's a quotient, p of z over q of z, quotient of two polynomials with no common roots. Okay? So that relates to configuration spaces because you're determined by your roots, so I can keep track of, it's the same thing as sort of actually secretly like configurations of two sets of unordered points, two sets with d things each. I'm keeping track of the d zeros of the numerator and the d zeros of the denominator. So the d zeros and the d poles, and they can crash into each other, but they can't, each type, but they can't kill each other. Yeah. But it's this, and in fact, right, this embeds into affine space, which is just the field. You know, this is the vector space, but this is a better terminology for various reasons. By taking this tuples of polynomials to just, you write down their coefficients. A10, sorry, A10, A20, AD0, then again, A11, all the way to AND or something like that. Yes, AND. You just write down all the coefficients of all the polynomials. And that gives you a map here. And you need some condition. You can't, that's not a surjective map. I need to write down the condition that you don't have common zeros. And it's really cool. The condition that a collection of polynomials not have any common zeros, common meaning they, you know, this point is a common zero if it's a zero of all my polynomials. The condition on that is a polynomial in the coefficients. It's called the resultant locus. So rat star d of n is a d to the n plus 1 minus, I'll call it the resultant hypersurface. It's one single polynomial. It's one huge polynomial, hypersurface. Hypersurface just means it's the thing cut out by one polynomial. Okay, so this means, and it's defined by injury coefficients, so these are algebraic varieties over z. The coefficients are z, and so you can look at it through all these different glasses. Okay? How the project started was Jesse and I, he's an NSF postdoc with Benson, so, but he was starting to talk to me about these spaces. I said, why don't we teach a course? I'm supposed to teach a course. Why don't we do joint lectures? Which ended up being him doing all the lectures. Read Siegel wrote a very famous paper where he looks at the topology of these spaces, the integral homology. And he shows that it's stably, the homology is the homology of loops 2 of S2, and he's a topologist, and okay. So I'm like, let's try to do a point count, because these are varieties. If you can tell me the cohomology stably, and that's that second line. Homological stability should give asymptotic point counts. So I said, let's do that. But there are these things hidden in there. You have to bound how the Beatty numbers grow, and we're getting bogged down. It was like very difficult, and we're getting stuck. And then we realized somehow, like, this is looking like this motive stuff. Maybe that's useful. And like, within one day after we realized it, within 10 minutes after realizing this, we weren't able to prove stability for the rational cohomology. You just need rationally. As you know, we only care about rational cohomology just for point counts, even though integral has lots of other information. For algebraic geometry currently, up until the last few years, we care about rational cohomology. We're like struggling with the Beatty numbers. After motives, we computed all the Beatty numbers dead on, not stably. And I'm going to give you the computation. You should be able to do it after I give you the toy computation. We read a blog by Jordan Ellenberg for a teeny special case. And he just said one word. And it's just, so the theory of motives to us was like, okay, it took us from like struggling for a 10 times weaker result to like instantaneously getting a thing So then we were convinced. And we've been on this odyssey ever since, like brutally exploiting this in every possible way. And it's really exciting because we're hitting lots of really cool issues. I don't want to explain that to you. Let me just say, though, one other cool set of varieties that we're looking at, SPND. This is Vassiliev terminology, symmetric products. This is the space of monic polynomials. This is sort of what people might call the stratification of the discriminant locus in polynomials, but such that P has no roots of multiplicity greater than or equal to n. So, for example, having no roots of multiplicity 2 or more, we've seen that. That's called poly D. But then I'm allowing roots to have multiplicity 2, but not 3 or more. 2 or 3, but not 4 or more. So these are very complicated varieties. I'll just say the punchline, they're like a to the d minus something called the discriminant hypersurface. They've been an object of study for a long time, but especially by Vassiliev and Arnold and those guys. It's an algebraic variety over Z. Same as before. Great. So let me give you, don't want to give the theorem. Okay. Yeah, before I give our theorem, I need to tell you, what the objects are in the theorem. So those are varieties. Any question? We wanted to understand these as examples, and again, proofs of concept. So I want to talk about the Grothendieck ring of varieties. I will remind you, this occurred in Ravi's talk. Oh, did I make a boo-boo?
The monic PFD equals some terms rather than plus.
Sorry. P of z equals, yes. Thank you. Thank you. Yes. Okay. But any questions? These are very basic and important varieties. And we wanted to understand many things about them. But for example, the point counts are always a good thing. No, this is just poly D, sorry, poly sub D, yeah. Okay, I want to talk about the Grothendieck ring. So when I talk about motives, to me I'm going to use the word motive for the Grothendieck ring. I'm going to use the word motive for elements of this ring, but what's really happening is this ring is just a kind of baby version. The problem is, the actual version, I think, is a lot harder. I don't know anything about it. But.
You mean mostly conjectural?
Yeah, mostly conjectural. It's mostly conjectural. Mostly conjectural. So it's not me. Good. I'm sure it would be me if they could do stuff, but yeah. No, I mean, they could do a lot. But K is a field. And let var K, I'm just recalling what Ravi Vakil did in his talk. This is the category of all algebraic, maybe singular, and maybe algebraic varieties defined over K. And the maps are algebraic morphisms. And then you define the Grothendieck group. I'll just say the Grothendieck ring, because it has a ring structure I'm going to say within 1 second. The Grothendieck ring, it's K0. It's such a great idea. K0 of Rk. It's defined to be the free abelian group on the set of varieties over K, by which I mean isomorphism classes of varieties. It's isomorphism classes of varieties. So let's just ignore that thing. Satisfy, so modulo two relations. This is the scissors relation. It's a cutting and pasting that the class of x minus z, so if z is a closed subvariety, or even just locally closed subvariety of x, it's z, sorry, this plus z minus, can I possibly be more confusing? I want this to equal x. So I'm going to mod out by that. So any questions? It's like a free abelian group. I can do this. It's this crazy ass stuff, but it gives you, yeah. And then the multiplication, as Ravi said, is x times y is you take the product, class of the product. And this makes this thing into a ring. So you just plug in a field, yeah. And it's all varieties of all dimensions and everything, yes.
I guess you probably want like free abelian group on isomark.
Right. That's what I said. Yeah, I said. Yeah, I said that. So, okay. So let me just point out, anything times a point is the thing. So 1 is the class of A0. A again is just the field. You can think of A as just K. Think of the affine line. And 0 in the ring is the class of the empty variety. Okay. Why do you do this? This is based on the amazing fact that it is a miracle. By the way, for people who are in my class when I was talking about this, and Shmuel Weinberger was there, and he said, it's not as much of a miracle, and there's a theorem of Weinberger. That only works in a complex case. So you need resolution of singularities for what I'm about to say. But it was proved, at least in characteristic 0, it was proved by Hironaka. And she was 5 years old. It's totally true. Echo is only 5 years old, and Hironaka actually proved this. But I hear Schultze is better. No, he was better when he was 5. Sorry. So all I want to do with this is a whole thing, but all we're going to do with it today, there's a whole list. Amazing, I would say, one fact is amazing and one fact is trivial. But you will appreciate, hopefully. The idea of this is that if you look at, suppose I ask you, how many points does projective line over FQ have? Or the projective n space over FQ? We could all do it. You're doing a point count. And I ask you, how about compute the cohomology? Yeah, we have this big fancied thing between them, but guess what? Like literally your pieces of paper, I could cross out your cells and put just like a Q to the whatever. It's like the same computation, formally. So how do you like formalize that wacky dream that those things are the same because the computations are the same? It's this. Or at least this is the toy case. There exist ring homomorphisms. I mean, there's a long list here, but we're going to do 2 of them. So this, I think, is a miracle. I'm going back to the miracle. Or a theorem of Weinberger, which is, yeah. To Z, I can take the class of a variety and then just take the Euler characteristic. This is absolutely false for when X is a circle and Z is a point. I mean, Euler characteristic doesn't work like how do I do the Euler characteristic of a space? I just take a closed subset, rip it out, and it's like the disjoint union of that closed subset and the complement. Like the Euler characteristic of that plus the Euler characteristic of this. Right? It's like Euler characteristic for like kindergartners where they're wrong. And they're wrong for the circle with a point. Euler characteristic of a circle is 0, of a point is 1, and of the complement of a point, it's 1. Right? Because it's a cell. So 1 plus 1 does not equal 0. For varieties, it works. For all algebraic varieties, including singular varieties. That's definitely a miracle. Although, yeah, we can talk about it after. Number 2, here's I read a paper, somebody referred to this as the motivic blah, blah, blah. Ready? There's a homomorphism. Ready? Cannot. They really did. They really did. There's a thing from this Grothendieck ring where you take the class of a variety to Z, and you just take the number of points. I've been writing it slightly differently, but the number of FQ points, say. You can take the number of FQ to the D points for fixed D. But ready? We can all prove this. That this is a ring homomorphism just says, so this one was a miracle. The Euler characteristic of X minus Z plus the Euler characteristic of Z equals the Euler characteristic of X. What? Yes. No, Mayer-Vietoris doesn't give that. Here you have a set, a finite set, and it's a disjoint union of 2 other finite sets. The cardinality of this plus the cardinality of this is the cardinality of the whole thing. theorem. It's the theorem of Wolfson. I'm going to make him look bad. Yeah, he submitted that to the annals. No. There's other things for experts. There's a whole bunch of things. There's like Hodge polynomial. There's other things. But I just want to get just these two. Why is this helpful to us? I'll tell you why. Now I want to give our theorems and then try to explain at least a toy model for the proof. Can someone tell me how much time is left? Sorry? Okay. An hour 24? Okay. Okay, the theorems. Theorems. Good. Theorem 1. And it's Farb and Wilson. These are all extremely recent, and everything is in flux. But let K be a field. Probably we want a perfect field, but anything that's not like a function field over finite field. Let K be a field. Then what we computed is this. This is the space of holomorphic maps, degree D, from P1 to Pn. It's an algebraic variety. On this side, it's A, D. It's just affine space minus another affine space, D minus 1, M plus 1, plus 1. And this is true for any field. Varieties. 2. And we did these other guys, these like very complicated guys. So this is sort of crazy because, okay, that's a statement of theorem 1. And I want to say, like, this has fundamental group, it has tons of topology. The spaces are very different. This is super different. This has like higher homotopy groups. This is just like a line minus a lot, affine space minus a smaller affine space. They're very different. We did so many violent things. But then as a corollary, well, you can get point counts because, ready, the number of things in affine n space is q to the n. So as a corollary, you've counted FQ points on these instantaneously. You figure out the Euler characteristic. But I'm going to show you how you can extract the cohomology, actually, each individual cohomology group. The Euler characteristic is much coarser than cohomology. But I just wanted to say, remark, just because it's sort of fun, is that rat d star of n equals, and here's how the numbers work out. So these spaces have been studied by many people, and these two spaces are known to be homotopy equivalent by like Cohen, Mann, and Milgram, based on work of Vasiliev. Or maybe I'm mixing and matching, but it's a bunch of people. They're homotopy equivalent, which doesn't mean anything. Let me point out that affine 500 space is homotopy equivalent to like a point. But the point count is very different. So these are hugely different in the ring of varieties. How do you prove that? Because the point counts are different. The ring homomorphism, if they were the same in the ring of varieties, they'd have the same point count.
They're only stably homotopy equivalent in the like lowest case timeline. Right.
Oh yeah.
As soon as
For n greater than or equal to 2. So I just wanted to pose this to the audience. And this is one cool thing that you can get from the theory of motives. There's all these predictions. Are these, the question is, are these like isomorphic as varieties? Is there like a biholomorphic map that would do it? That would explain everything. That would explain the topological results of these guys. And it would explain our result. And this hints at it. But if you look at the way they do it, it definitely doesn't give any algebraic map between them that you could try to check or anything. Or it's very non-algebraic.
They're not homeomorphic, are they?
I don't know. Are they homeomorphic too? Right.
I haven't seen anything to that effect. I mean, like, right now, they're like, Cohen and collaborators like use scanning compared to like a third almost space.
Yeah, so actually, yes, homeomorphic would be a first problem. But this would indicate that the reason, and this has happened before with many other people and with us, is that this gives you like a reason that you would expect that you wouldn't otherwise like realize there's such a map. So theorem 2 And I'm just going to state it just to save time here, because I'm running out of time, for rat star, just for rat star D. But we have the space of holomorphic maps from P1 to Pn. We have it for these other spaces of polynomials. You have the following things. I would call this the FQ, looking at the rat D through the FQ glasses. I mean, my favorite part is for n equals 1. That's just this hugely studied thing like rational maps on the two-sphere. And that's like what complex dynamics is. And so with FQ glasses, we get, of course, I'm just plugging in the number of FQ points, of rat D star is the number of FQ points, so it's Q to, it's like just an exact count. So you can see hopefully see why we're like enamored of this, because we were like super struggling to prove that. But like, if this is true, if stronger things are true, they're easier to prove. When you look at it with like FQ bar glasses, so this is a little bit for the experts. One of the things that number theorists spend tons of time on is understanding the eigenvalues of Frobenius on a tall cohomology of rat D star. Sort of as a variety over FQ bar and L-adic. This is sort of for the experts. Remember I said God is coming down and giving us these, like it was Q to the minus I or something for polynomials. I just said that's a really tough thing. I want to advertise to people in the audience that even we topologists can actually compute weights. These are called weights, like the eigenvalues of Frobenius. And we can do it. I'm going to do, hopefully, if I have time, I'm going to do it for you. Purely from topology, using the theory of motives, has eigenvalue. It's Q to the minus I in degree I, of course, if n is 1. And this is a cool thing. There's a shift. This is a sort of slightly cool thing, because it's not pure. It's a shift. Q to the minus I plus 1 over 2 if n is greater than or equal to 2. And finally, if you look at things with complex glasses, with topology at least, or then you get this theorem. They proved a stronger theorem than this. Cohen, Mann, and Milgram. They proved, I think, did they do stable homotopy equivalence? But we can get that the Beatty numbers are equal to, is 1 in 0 and 1, and 0 if I is bigger than 0. 2n minus 1. Thank you. That would really have messed me up later. In degrees.
I is greater than 0.
And I is an else. Yes. Thank you. And 0 equals 1. I'm announcing 0 equals 1, and I'm due to Wolfson. Like, how to screw over a young collaborator. Just start like spouting nonsense. Okay, so what I want to do, and see, great. I want to, I think, give you a toy computation. But the goal of the rest of my talk is two things. I don't know if I'm going to be able to do it.
Is there a reason why you write the number as p minus 1 times n plus 1 instead of p times n plus 1 minus 1?
Oh, no. It's just, right, yeah. I think it's just the way it was proved. It sort of comes out this way, by the artifact of how we're proving. Like the way I'm writing the numbers. Yeah, and I think hopefully you'll see this. But the two things, in case I don't get to them, I definitely want to do this toy computation for all of you. That then you'll be able to at least prove some of the stuff. But you'll get the flavor of how it works. I'm going to do a toy case. But then I wanted to just say, Sean Howe commented with this very, very beautiful triangle of cohomology and I'm always forgetting the things of the triangle. I feel like there's three parts of the triangle. I am the, what's this, yeah.
So it's theorem 2, like, it's not a corollary of theorem 1, right? You have to do some more work to get theorem 2.
Yes. But in theorem 2, what I want to do, I wanted to talk about the triangle Sean Howe was talking about between understanding point counting, Frobenius, eigenvalues of Frobenius, and Beatty numbers. if you have any 2, you can get the third. He was sort of saying this in his thing, this triangle. And like, we can do that. Like, we can do this by hand. We know this just from our Theorem 1. Just to answer Sandra's question. We know this from Theorem 1. Then, if you can do this, which we know how to do by hand by trickery, this plus this, we get a new proof of Cohn CCMM in the rational case. If we're willing to quote CCMM, that plus this gives this. And I want to do those. But it's totally elementary arithmetic. But I want to do the toy computation. Proof idea. Proof of Theorem 1 in the toy case. In other words, so what is that? The claim is that poly n. Yeah, I definitely want to do this. It'll be disappointing if I can't do the other, but this one is the important one. Okay? So remember, when n is 2, it's like this is SP2n. Case. It's easier, but right. And this is this is sort of after Ellenberg and Zeev. Jordan Ellenberg had a great blog post. And he says, oh, Mike Zeev has a really cool thing that the square-free polynomials over FQ, remember I've been doing this over and over every day, the number of monic square-free polynomials is q to the n minus q to the n minus 1. And he's got this great proof, this clever proof. And Jordan just says on his blog, his point counting proof just proves in the ring of motives this. And Jess and I were like, huh, okay, let's do it if that's really true. And then we actually could do it instantly. And then we just went to town from there. So it was really inspired by these guys. And let me give the proof. I'm going to do one thing in the ring of motives here. Okay, excellent. So here's the key. And this is the thing that we're sort of exploiting. And people who know Siegel's paper will sort of get excited because they'll see what, because this is sort of the Siegel point of view. Look at the set of, what do I want to do? You have the set of all polynomials, all monic polynomials. So that's isomorphic. The space of all such thing is a to the n, degree n polynomials, with the following property. So I'm going to filter the space of all polynomials, right? If you have a degree n polynomial that's monic, I have to just tell you the n coefficients, like no conditions, right? All polynomials. I'm going to let dnk be defined to be, oh yeah, you factor every polynomial you can factor. F of z is h of z, g of z squared, such that h of z is such that you factor out all the things with multiple roots, so that you look at the polynomials where the where you look at all, you factor it out by like this, the things that have multiple roots and that have degree at least k, and this will be polynomials in L for some L. Poly is the distinct polynomials, square free. So you sort of take out the square free part, you write your polynomial as a square free part, and a part that has repeated roots. No repeated roots, and you filter it by the degree. Sorry, I should have just said that. So you have this thing which is like dn0, contains dn1, contains dn2, and it goes all the way down. Eventually you're going to get like the empty set, because when the degree is greater than a trillion. So, right, so you just like filter your space all the way down. I think it probably ends when like n comma n. Okay, and so this is a filtration. So there's a few comments. Note that dn1 is the set of polynomials with a multiple root. In other words, right? Because I'm saying, look at the set of polynomials where I can write them as some polynomial times something that's at least linear squared. So you have at least one root of multiplicity 2. So in other words, an, the first term, minus this is nothing more than poly n. That's the space we care about. That's the space we want to compute in the ring of motives. Any questions? And more generally, take a look for a second. This is a great trick. dnk minus dnk plus 1, more generally. So what is this? This is polynomials where this has degree at least k, but not degree at least k plus 1. So it's the guys that have degree at least k. So it's where you can factor where this is any polynomial of degree at least k. So how many are there? There's how many polys of degree at least k? The space of such things, right? What is the set of such things? This is any polynomial of degree k, so it's a to the k. And then times a polynomial without repeated roots. And its degree better be, if it all adds up to n, it better be n minus 2k. Because you're squaring the other. Any questions? So this gives a recursive formula. Look what this gives. Yeah, I think this is like totally awesome. Yeah, this is just taking the filtration. Yeah. Yeah, but let me just do this. So this implies, now just take everything. I'm going to write, whenever, this is the key word, filtration. Because when you have a filtration, you write this is equal to this minus this, plus this minus this, right? So I'm going to just, and disjoint union, so you write the following. You just say, look, an, and everything in sight, sorry, all of these are algebraic varieties. All these are algebraic varieties. See, even if you just cared about projective varieties, you're going to go outside the category. That's what this cutting and pasting, you have to be totally general. So once that's all set up, this is an minus dn1, right? Disjoint union, dn1, I'm doing something that's like you give to your non-math major freshman, dn2, etc., all the way down to...
I mean, this isn't like a disjoint union as varieties. Like, in the category of varieties, these are not a disjoint union.
No, but there's closed, locally closed subset, right. It's, one thing is like a locally closed, locally closed, locally closed, yeah.
I mean,
And so in the ring of varieties, what this gives you is that an, you're making my brain melt, is equal to, the first term we just said is the thing we care about, poly n, do you see? And then plus summation k equals 1 to infinity. I mean, it ends somewhere. I'm not going to care. I'm just like literally writing. And then each of these differences is this product. So it's poly n minus 2k times a to the k. This gives a recursion to solve for poly n because we know that like polynomials of degree 0, it's a0. So it's 1 in the ring of motives. If you look at all monic square-free polynomials of degree 1, you're just telling me it's z plus c, where c is a coefficient, so it's a1. And then you can see that, like, what's poly 2? Poly 2 is a2 minus poly sub 1 times a1, or times a0. And so it's this. And now you induct. Since I'm running out of time, I won't give the extremely pleasant recursion, but you should do it. So are there any questions? In other words, I induct, and by induction, this is supposed to be equal to a to the dimension minus a to the dimension minus 1, n minus 2k minus 1. I've now got, these are a whole bunch of affine spaces, and we know how to multiply them. This is affine, so I can solve for poly. That's it. We just did a computation in the ring of motives. And you can get like Arnold's theorem on the cohomology if you know the way. There's this 2 out of 3. So maybe I'll end, wow, how can I possibly do I would do all this stuff. No. But I just want to give one proof idea for theorem 2. And I will end. So it looks like I'm just going to get one thing done.
Yeah, so it will be A1 minus A2.
A1. No, this is the funny part. There's this funny little thing. Yeah, Shmuel Weinberger did this too. It's like, can you do that last thing? And it's like, wait, there's no A0, but that actually makes it all work at the end. Remember, I've been ignoring it with this infinity. So it's great. It's a telescoping. Yes. Right. Yeah, so it's, yes, when you want telescoping, but you don't want the bottom term, something has to happen down there to kill them. But this is like totally, literally 8th grade, you learn recursions like this. Okay. So I just want to get the idea that, the proof, in fact, that which way should I go? I just have to decide one. But I want to do number rat d star of n. I want to compute a weight for you guys. That's what I'll do. Instead of getting a new proof of Cohen, Mann-Milgram. Suppose we know, so I showed you 3 things in Theorem 2. One of them is the point count. That's immediate from the, you have to do this now for rat d star and the things I said, and it's more topology, but this gives the spirit. But I want to prove that suppose you know that the number of points here is q to the d times n plus 1 times 1 minus q to the minus n. That's what you get out of it. And suppose you also know that the ith Beatty number, this is Cohen, Mann-Milgram. Suppose I want to quote them to get what these eigenvalues of Frobenius are. And what's great is you literally, I didn't even tell you what a tall cohomology is, but you can still compute the weights just like we did. B of rat d star, the space of holomorphic maps from P1 to Pn, they show it's like the Beatty numbers is 1 if what I say I is 0 or 2n minus 1, and 0 else. This plus this, I want to say, implies, and let me just do n greater than or equal to 2, that the eigenvalue of Frobenius acting on cohomology, on the ith degree cohomology, there's only 2 non-zero degrees, and in degree 0 you always act by 1, so I'm really just telling you what is the eigenvalue on this one-dimensional space. Let me just emphasize, Frobenius does not act on the complex points of the manifold. It only acts on this étale cohomology. But let me just show you how the Grothendieck-Lefschetz gives it. When hi is equal to whatever it is, whatever it equals, and I'll give the answer in a second. How do you figure out what it equals? Here's why. So proof. I didn't give the theorem yet. I have to tell you what this equals. It's q, what did I say, q to the I plus 1 over 2? Or minus I plus 1 over 2? Right? So it's an interesting case even. It's not sort of, the standard thing is like q to the I over 2 for projective varieties. So here's the proof. Grothendieck-Lefschetz formula, and this will be the end of my talk. The Grothendieck-Lefschetz formula gives, let's just do the formula. It gives on the one side the number of FQ points, which of course is, we just said, it's q d n plus 1 times 1 minus q to the minus n. And on the other side, it gives, there was Poincare duality, but the formula read like this. Q to the d to the n plus 1 times summation minus 1 to the I I only have 2 Beatty numbers, right? So sorry, it's like some étale cohomology groups, but everything has dimension 1. Remember, it was like some eigenvalue. It's a 1-by-1 matrix, the trace of a 1-by-1 matrix, since these are just dimension 1. So the eigenvalue is the matrix, and they're one-dimensional. And so we just need to know, I'm giving you that this plus this, yes. And so all it is in degree 0, I know you act by 1, and then in minus some mystery thing we're trying to solve. This is the eigenvalue. And it's acting on h to the, what did I say, 2n minus 1? So I now want to say in terms of I. So what happens is this crosses out on both sides. The 1s cross out. So it turns out that that lambda, so on 2n minus 1, if j is 2n, so this is the this must be the eigenvalue. So if j is 2n minus 1, that's the degree we're in, or I. I is 2n minus 1, so n is I plus 1 over 2. And so the eigenvalue lambda is q to the minus n, which is q to the minus I plus 1 over 2. I'm just saying that lambda has to be this. And this is true for all q. So I just determined that you must be acting like this to make the Grothendieck-Lefschetz formula hold. It's not, it's like literally my daughter could do this. She's very smart though, but she doesn't know the background on motive. But you see what I'm saying though? We don't need to even know about, so it's just that this triangle of Sean that he was saying, yes, these are, you really can, in practice, and this is what we've been systematically doing too, for all over the place, in practice, getting two parts of the triangle. The triangle being point count, cohomology, not the Euler characteristic. We know the Euler characteristic once you get that. So motives are sort of in the middle of the triangle. Euler characteristic to cohomology is a much more refined thing. But if you know the point count and you know the weights, you get this. Exercise. It's the same, I'm giving another variable. So in summary, I hope I've demonstrated that like just this whole huge picture, I just specialized for the first few days in like space of polynomials. Like ready, there's a theory. The theory is you have sequences of algebraic varieties coming up all over mathematics, like spaces of holomorphic maps and spaces of hypersurfaces and all these kind of things. Why do we care about these spaces? Why do we care about their cohomology and their point counts? I'll tell you why. That was the first few lectures. McMullen's work, solving the Quintic, concrete applications of the topology. I then tried to show how do you get access to this stuff? Well, there's the three levels. There's understanding the cohomology of one thing, understanding the cohomology of the sequence like stably, classical homological stability, and understanding the two columns that I just gave. Representation stability gives like weighted point counts, the bridge. Today's talk was like, look, there's two things I want to say. All of that was so incredibly rich just for the space of polynomials. There's all these other spaces. Of course, people have been working on their cohomology. You know, topologists have been working on their cohomology. But there's all the rest of the story. What is McMullen's theorem for the space of hypersurfaces? What does it mean to not solve the Quintic? What is the lessons we learned there? What does that tell us about hypersurfaces? And secondly, all of this picture should all be one big consequence of some motivic picture, where just for a cohomology group of a single variety you have a motive, which is what I did today. Then there should be some kind of homological stability in the category of motives. And there's a paper by Vakil Wood, so this is a very, very new thing, and it has mostly speculations and some, and there's work by, we're going to hopefully hear about by Coopers and Miller, but it brings up interesting things in topology, but this is like stably motives, and then there should be representation stable motives, FI motives, and that really is a concrete goal. And what I like about it is, you don't just make up a theory. You shouldn't, just make up a theory. What do you want it to do? Like, what is a theory of like SN motive? You know, people do make up good theories of that are useful. But to me, it's like, ready? It should pop out this representation stability stuff when you plug in poly n. If you can do that, you've got the right theory of FI motives. If it's like telling you all the way down here. Anyway, so that's what I want to, thank you for listening to all the talks, or for attending all the talks. Oh! Sorry.
Your questions, Benson.
So you said you can get a different mirror improvement of CCMM. So how do you compute the eigenvalues of Frobenius without?
Whoa! I will just say this. Let me do it in the toy case of poly n. How do you compute eigenvalues of Frobenius in the space of hyperplane arrangement? This is due to Lair. But here's the trick. You look at the cohomology of it's harder, but you can do the similar thing. The question is, how do you compute eigenvalues of Frobenius on some space on the space of polynomials? Well, it's covered by configurations of endpoints. And if you knew eigenvalues of Frobenius up here, if you knew they're all the same, then the SN invariant part of the cohomology, so it's transfer. So how does that help? If you have a hyperplane complement, as Arnold showed, in the space of ordered tuples of points, all the cohomologies generated degree 1. So I knew it all acted by Q, or Q inverse, right. Q to the minus 1, I'd be done. But look, you look at each of those, you got to get into the geometry. You look at each of the forms that generate H1, like its differential forms, with those things, and you say, oh, they're all pullbacks of forms from configurations of 2 points in the plane. Conf 2, so you pick the I and the J, and in conf 2, that happens to be C star, the complex plane minus a point. That's where you can compute by hand eigenvalues of Frobenius, and it's Q.
I see, okay.
Yeah, and so in general, we need to do like, it actually, Bjorn and Rekdal worked on this, but I think we can use this trick to give a quicker proof of them. Their thing is for linear subspace arrangements, at least in the special case of Bjorn and Rekdal where they're all the same dimension. But actually, I think we're going to get the whole thing. This kind of thing, you like show where cohomology, have simpler models where you can do it by hand and show your things are pullbacks from them. Yes?
Also, I have a question about the common set. So for the point counts and eigenvalue of Provenience and Betty numbers, so the claim is if you know 2, you can write third.
Sorry, that's not, sorry, only in very special cases. Here we're really using that you have cohomology only in 2 degrees.
Okay,
Sorry. Yes, in general, knowing 2, yes, that was a mistake, a misspoken thing. With this triangle of these 3 things, 2 don't just give formally the third. 2 and like trickery or simple things like here, I really use the fact that like 1 minus blob equals 1 minus blob, so blob equals blob. If there were like 20 terms, then like you have to match them up. It's hard to know which things are, If you have a sum of 15 things equals a sum of 15 things, I can't say each individual thing here is each individual thing here. But you can, there's lots of trickery to do, because this stuff is true for all Q. So it starts being like, But it's hard, I am making all these miracles. I'm doing them in very special cases and making it seem much easier. There's brilliant people who struggle their whole lives to compute eigenvalues of Frobenius on it, I'm just like, la la la, isn't it? And like, we happen to be in some cases where you can do it. Right. I was doing that actually with cases where you can't do it, and then people are like, this is not easy, man. Yes?
Is there some like subcategory of varieties where you have another homomorphism that takes you to some kind of Euler characteristic for the real points on the variety with, say, Z-mod 2 coefficient?
I don't know. Does anybody know that? Do you know this, Jesse?
I think how you try to prove it is just show that satisfies the relations you're using. And I think what you're saying with Benson's computation of circle breakdown, that looks like that would work, but you have to.
Right.
I'd have to just be
There's no version of cohomology that fixes it?
No, I think these 2 coefficients might actually, but I can't think that.
Right. There's more things here too. You get the Hodge polynomial for smooth and projective. Yeah. It'll be very interesting, especially too. Vasiliev is really, and his method absolutely applies to like real hyperplane arrangements and lots of like real discriminant locus, real polynomials. He has this whole book, as you know, and so as long as you have this set up, it should work. Yeah. Anyway.
Okay, let's thank Benson again for a wonderful.